Welcome to our discussion of more trigonometric functions, trig equations, part 2, electric boogaloo. All right, what are we going to do this time? We're going to solve some trig equations by using the identities, and then we're going to tackle some equations where we have multiples of angles. So instead of just sine of theta, we'll have sine of 2 theta and 3 theta and things like that. So as before, we've discussed this. We always want to try and use the identities whenever possible to simplify things. If that doesn't work, oftentimes it's beneficial to replace all of your trig functions with sines and cosines, right? If you have a tangent, you put in sine and cosine and secants and things like that. Put everything in terms of sines and cosines, and then often a lot of stuff will cancel out and reduce down that way. And then if you have multiple angles and things like that, that's where you start using double angle formulas, half angle formulas, power reduction formulas, and so on and so forth. Okay, so let's look at some examples where we're using identities. If we have 2 sine theta minus 1 equals 0 or sine theta plus 1 equals 0, it really doesn't change what we're doing. As before, you isolate your variable, right? In this case, it's theta, so you move the 1 over, divide by 2, blah, blah. We've seen this before. Simple, easy, and we get these simple solutions with adding on the 2k pi for the periods. Well, what happens when instead of our trig function equaling a constant, we now have a trig function equaling another trig function? We basically have two different trig functions, right? If this was all a bunch of cosines, that'd be easy. We could add them together or cancel them out or whatever we got to do, but now we're stuck with a cosine and a sine, and that's no good. So what do? Well, start thinking about, well, we have various things that relate a trig function to another trig function, right? We can list cosine of 2 theta in terms of other things. We can list cosine of theta plus pi over 2 in terms of sine. But we can't just switch cosine of theta or sine of theta. It would have to be those pi over 2 cofunction things, and we don't have that. Okay, so what other things do we have that relate sine and cosine? Well, we've got the Pythagorean identity. Well, I don't have sine squared and cosine squared. Okay, easy problem to solve. Just square both sides. So I'm trying to walk you through how you can kind of think your way through how to solve these types of things. And it's all about you have a limited number of tools to tackle each job, each question. And it's just a matter of kind of going through that Rolodex of tools and going, which one fits? And in this case, we got to use the Pythagorean identity. That's the only way that we can kind of sub out a cosine for a sine or vice versa. And since things aren't squared originally, we go ahead and square them. So if you square both sides, right, cosine plus 1, you get cosine squared plus 1 squared, and then plus 2 times their product. So there's where you get the cosine squared plus 2 cosine theta plus 1. And then, of course, sine just becomes sine squared. Easy, simple. Well, since we already have that 2 cosine theta piece stuck in there, there's really nothing we can do with that. So we're kind of forced to put everything in terms of cosines. So let's take sine squared, use the Pythagorean identity, swap it out for 1 minus cosine squared, do some simple algebra, put everything on one side set equal to 0, and now we've got a quadratic. And we can solve quadratics. Because really, this is just 2x squared plus 2x equals 0. And we don't even have to treat that as a quadratic. We can just pull out a 2 cosine theta, right? You just factor that out. And now you're left with 2 cosine theta times cosine theta plus 1 equals 0. So each piece has to equal 0. So either 2 cosine theta equals 0 or the cosine theta plus 1 equals 0. Right, divide the left side by 2, so cosine equals 0. We know cosine equals 0 at pi over 2 and 3 pi over 2. On the right-hand side, we move the 1 over. Cosine has to equal minus 1. That only happens at pi when we're talking about within a full period of cosine. And then add the 2 pi, right, the 2k pi's to the ends of them. But before we do that, you always have to go back and check to make sure that everything works in the original equation. Because when you change these things around, it's just like when you square, well, it's exactly like that because we squared both sides, right? If x equals 4, and then you square both sides, you now have x squared equals 16, right? Okay, now to solve for x, you take the square root of both sides, but when you take the square root of a square, you're supposed to do plus or minus. So technically that gets you back to x equals plus or minus 4. So the math ends up giving you two solutions when we know we started with only x equaling 4. Now that's a simple, stupid example because you would never do that because, if x equals 4, x equals 4, why would you? But I'm using it as a point. Because we squared both sides, we introduced the possibility of a second solution that might not work in the original equation. So we have to try them. So we take all three of those solutions, pi over 2, 3 pi over 2, and 0, plug them into the original equation, and make sure it works, right? The original equation was cosine theta plus 1 equals sine theta. So you put in pi over 2 and pi over 2, and it works. You put in 3 pi over 2 and 3 pi over 2, it doesn't work. You put in pi, and it works. So that tells you those are the only two answers. And then you would slap the plus 2k pi's onto the end of those two. All right. If we want to find intersection points, we can look at the graph and do tracing and things like that. Or we can try and solve it algebraically, right? So if we want to use the trace function, we can do that, and we can get kind of an approximate. But if we want to actually solve it, we have to do some algebra. Well, this is kind of easy, right? Because if sine x equals cosine x, you think about, well, wait a minute. If I divide both sides by cosine, then I get sine x over cosine x equals 1, and sine over cosine is tangent. So this is really just asking for tangent equals 1. And now if we look on our unit circle, we know where tangent equals 1. It equals 1 at pi over 4, and then also around the corner in the third quadrant at 5 pi over 4, but that's really just pi over 4 plus k pi, because remember, tangent has a period of pi. So these are all the solutions where sine x equals cosine x. And if you do pi over 4 in your calculator, you'll get that first example of 0.785-ish. And then if you do, right, if you add pi to it, so you add that first k pi, so let k equal 1, and add 1 pi to it. So you're basically adding 3 to it, and that's where you get the 3.927, right? Because pi is really 3.14, blah, blah, blah. And you can see that it gets you up there to about 3.927. So that's all those are. Those are pi over 4 and 3 pi over 4. I'm sorry, 5 pi over 4. Okay, how about if we tackle equations with multiple angles, meaning 2 theta, 3 theta, things like that? Well, actually, it's just as easy as solving the other ones, because all we do is solve it as if it was a theta instead of 3 theta or 5 theta or theta over 2, right, or anything other than just regular old theta. Solve it as if it was normal, figure out what theta is, and then now figure out what the actual angle is. And it'll make more sense when we do one simple example. All right, so here is 2 sine 3 theta minus 1. What we're really going to do is we're going to treat this as if we're really just solving the equation 2 sine theta minus 1 equals 0. So we add the 1, right? Then we divide by 2. And we go, oh, well, sine equals 1/2 at pi over 3, and then around in the second quadrant as well. So in our picture, sorry, not pi over 3, pi over 6, and then around the corner at 5 pi over 6. Those are the two places where we get the height of sine being 1/2. But that's not really theta equaling that. Remember, our original one was sine of 3 theta. So that just means 3 theta has to equal those. Well, if 3 theta equals those, What do you think theta equals? Well, duh, just divide both sides by 3. So 3 theta equals this, divide by 3, and we just get this. Now don't forget that you also have to divide this thing, right? So instead of adding 2k pi to it, you're adding 2/3 k pi to it. Because if we're taking a trig function of 3 theta, instead of having to go all the way around 2 pi to get a full revolution, as soon as theta is bigger by 2/3 pi, you multiply that by 3, and that becomes 2 pi, right? So it makes sense that that period multiplier is now 2/3 k pi for both of them. And from that, we can see if what happens when k equals 0, k equals 1, k equals 2, and we could list out all of the solutions within 0 and 2 pi, right? Because of that 3 theta, we're actually going to get multiple solutions, not just the first two, within that first 0 to 2 pi interval. And oftentimes that's what we're concerned with. It's like, how many times is this equation true in one full period of the function? And if we're dealing with sines and cosine, that means within 0 to 2 pi. And if we're dealing with tangent, we're talking about from 0 to pi. So in this case, we would list all 6 of those. Even though they're really just multiples of the first two, you'd still most likely list all 6. Okay, one last example. What if we have this? Well, again, it doesn't matter that it's theta over 2. You're still just solving for that angle. So you'd move the 1 over, right? Then you would divide by the square root of 3. Then you'd figure out, when does tangent equal 1 over the square root of 3? And that happens at pi over 6. And that's the only time it happens, because we're limited from 0 to pi. And so because that's the period for tangent, from 0 to pi. And in the first quadrant, tangent's positive, but in the second quadrant, it's negative. So there can't be anything over there. So it's only going to happen once at 1 over root 3, or square root of 3 over 3 if you are, 1 over root 3 happens only once at pi over 6. But again, that's not theta, that's theta over 2. So to solve for theta, you multiply both sides by 2, and you get theta over 3 plus 2k pi. Because remember, you gotta slap on that period repeater before you solve for theta, and it gets multiplied or divided by whatever you're doing, just like the other piece. Because all this is an equation. This is an equation. Theta over 2 equals all of this crap. And so if we're going to solve for theta, we got to multiply all of this crap by 2. And there it is. Pi over 3 plus your 2k pi. Now the last part, they wanted you to find all solutions in the interval 0 to 4 pi. And if we're going to go from 0 to 4 pi, k can only be 0 or 1. Some of you might be thinking, well, why can't k be 2? Because then that would give me 4 pi. But that would put you beyond 4 pi, because that would be 4 pi plus pi over 3. So in order to check that full 2 pi range, you can only let k be 0, which gives you the first way around. And in that first way around, we only had one solution. Then you let k be 1, which gives you the second way around, which is that second 2 pi rotation. But in that second full 2 pi rotation, again, we only get one more solution. So you have pi over 3, and then you add 2 pi, right? Because when k is 1, you add 2 to it. 2 pi, which is really 6 pi over 3 when you want to do a common denominator. And 6 pi over 3 plus pi over 3 gives you 7 pi over 3. And there are your only two solutions within the entire interval 0 to 4 pi.